Let's continue this discussion looking at this diagram. And what this shows you is a comparison looking at the difference in electronegativity and then what type of bond is formed. So if there's no difference in electronegativity between two atoms that come together, then you have what's called a pure covalent bond. This would be, for example, if two chlorines come together to form a chlorine gas molecule. If there's an intermediate difference, then you would have what's called a polar covalent bond. And then if there's a large difference, it would be an ionic bond. Now, if you move over to the right side, you can see that there's never an absolute no difference. And so it turns out that it's sort of a relative difference in electronegativity. So anything less than 0.4 is felt to be mostly a pure covalent bond. Between 0.4 and 1.8 difference in electronegativity is a polar covalent bond, and obviously the more toward 1.8 you go, the more polar it is, and the more toward 0.4 you go, the less polar. And then anything over 1.8 is thought to be consistent with an ionic bond. And what this arrow shows is that, in the middle here, shows is that this is sort of a continuum where covalent character increases, or ionic character increases as the electronegativity difference increases, and the covalent character decreases as the electronegativity difference increases. And so that's what it says at the bottom here. As the electronegativity difference increases between the two atoms, the bond becomes more ionic. Now, covalent bonding results in a different set of characteristics for the substances that are formed. First of all, these substances can be either gases, liquids, or solids, but the solids that are formed tend to have a low melting point. Now, this would suggest that there are lower or smaller intermolecular forces between these molecules. The liquid states do not conduct electricity. They are generally insoluble in water, and aqueous solutions of these substances do not conduct electricity either at all or well. And unlike the ionic substances, these will dissolve in nonpolar solvents. And this will lead to something we'll talk about in the future, which is the little adage, like dissolves like, and unlike are insoluble. So like dissolving like means that if you have a nonpolar solvent and a nonpolar substance, they will dissolve each other. And if you have a polar solvent and an ionic substance, they will dissolve each other. And these pairs, the sharing does not necessarily just one pair of electrons. It can be one pair, two pair, or up to three pairs of electrons, in which case you have a double, triple, or single bond. The last of the three chemical bonds that we'll talk about is the metallic bond. This bond occurs when atoms come together and they sort of contribute electrons to a general pool of electrons. And so they're sort of like ionic bonds, but the electrons are not localized to one pair of combining atoms, but all of the atoms come together, and at the same time they just kind of dump their valence electrons into this electron sea, and the electrons become delocalized so that you can't identify what electron came from which atom. This is a type of sharing, but it's different than the covalent bonding because the sharing is much more general. It's most commonly seen when metal atoms bind to other metal atoms. And it occurs with atoms that have similar electronegativities, but generally have low electronegativities, so that instead of the covalent bond where the atoms both have high electronegativities, in this case they're similar but they're low. And the properties of these atoms occur because, or these compounds occur because of the delocalization of the electrons. So for that reason, they are very good conductors of electricity. If you can imagine a substance that has electrons just freely moving, when electrons are added to that substance, they move right through as part of the delocalized pool of electrons. They are good conductors of heat. They are both malleable and ductile, which means they can be bent or hammered into shapes, and they can be drawn out into wires. They are frequently shiny and reflective, and they also have high melting and boiling points, which suggests that when this occurs, the intermolecular forces are quite strong. So here's an example of what I'm talking about the delocalization of electrons. You can see this is supposed to represent gold, and on the left here you have many gold atoms with their positively charged nuclei, and then there's this sea of negative charges which represents the electron sea, and you can see that no electron is particularly associated with any particular atom. And so if you look at figure B on the right, you can see why this would tend to conduct electricity. If you add negative charges on the left, you can see that very quickly the positive charges are allowed to move out on the right. Similarly with heat, you can see that these atoms, while close together, are close together, but they are also freely movable, so they can transfer the kinetic energy across from atom to atom. And then the part D is supposed to show you how they are bendable and malleable. So the top here shows the electron sea, and the nuclei just sort of disperse throughout this electron cloud or electron sea. Now, Lewis symbols are symbols that are used to illustrate the number of valence electrons for each element. And this table is taken the third period, that is the third row across the periodic table, and shown the Lewis symbol. It starts with the name of the atom, the electron configuration for the atom, which you already know about, and then the Lewis symbol for that atom. And you can see that how that works by looking at each of these. And so you can see what they've done with the electron configuration is use the symbol for neon to represent everything inside the 3s electron subshell. And by doing that, it just makes it easier for them to put it in this table. And you can see that the symbol plus a dot represents the sodium Lewis symbol and the one valence electron that sodium has. Magnesium and two dots represent the Lewis symbol for magnesium, and so forth. So we have the Lewis symbol for sodium, which freely gives up its electron and forms a sodium cation, as does calcium, which freely gives up both of its electrons to form a calcium cation. Chlorine, on the other hand, takes up an electron and forms a chlorine anion, and you can see how these are drawn with Lewis symbols, that once sodium becomes a cation, it doesn't have any dots, it just has a plus sign. Calcium has a 2 plus sign with no dots. Whereas when these anions take on their electrons, they're represented by additional dots as well as the negative charge. So if you're writing a Lewis symbol for an ionic compound, it would look like what's shown on the right of this table. You start out with the two atoms, the Lewis symbol for the two atoms, and then the Lewis symbol for the compound. Now, these ionic compounds have to be drawn this way. That is to say, you have to represent it as a sodium cation with a plus sign and no dots, and a chlorine cation with 8 dots and a minus sign, and this bracket helps you keep this straight, because if you notice the bottom row here where you have 2 fluorine anions, by using the bracket, you can just put a subscript 2 rather than drawing out both fluorine atoms or anions. If you want to draw out both fluorine anions, you can, but I suggest this form when I ask you to draw the Lewis symbol for an ionic compound. When chlorines come together, I said before that they have identical electronegativity, so they're going to form a covalent bond, and a covalent bond in a Lewis structure is shown like this, and this is a single covalent bond where you have two electrons there together between the two chlorine symbols. That represents a single bond. The rest of the electrons are shown on the outside. This can also be shown in this manner with a line that represents the pair of shared electrons. Hydrogen does not have any other electrons, so the pair of shared electrons is the only electrons that have to be shown, and they can be shown simply with this dashed line. The Lewis symbol for carbon tetrachloride is shown here. Carbon by itself has 4 dots, but it shares a pair of electrons with each of 4 chlorines, and so its Lewis symbol looks like this. And you notice if you look at just chlorine, it now has 8 electrons around it. It can also be shown with 4 dashes and the chlorines around the outside, with the dots around the outside of the chlorines representing the rest of the valence electrons. Silicon with hydrogen, silane, is shown this way. Remember, hydrogen doesn't have any additional electrons to be shown, and so the Lewis structure looks like the 8 dots around the silicon symbol, or it can be shown with the 4 dashes. The rule of octet is maintained throughout in virtually all situations. Now, there are very rare exceptions, which we may talk about at some point. The rule of octet states that the tendency of a main group of atoms to form enough bonds to maintain 8 valence electrons. You notice this tendency to desire, either through sharing or absolute transfer, to get 8 electrons around each atom. So here are 3 more examples. Ammonia has nitrogen with a pair of electrons that are by itself, and then 3 shared pairs with 3 hydrogens. Water is shown here with the 2 hydrogens bonding to the oxygen, and then 2 unpaired electrons. And then lastly, fluorine is shown here, and a similar symbol. Here's an example of 2 double bonds. With formaldehyde or formalin, you have carbon bonding to oxygen, but in order to get the rule of octet around both the carbon and the oxygen, you have to do a double sharing, so that there are 4 electrons shared between the carbon and the oxygen. And that sharing results in a double bond, which is shown with 2 dashes. And then the remaining 4 electrons are around the outside of the oxygen. Again, remember that hydrogen doesn't have any extra electrons to be shown. Ethylene is another compound that has 2 shared pairs of electrons, so a double bond between the 2 carbons and then the hydrogens around the outside. So what are the rules? Oh, before I say this, at the top here is an example of 2 triple bonds. Carbon monoxide actually shares 3 pairs of electrons in order to get the rule of octet around the carbon and the rule of octet around the oxygen. So does cyanide ion, and the ion has an extra electron in order to fulfill the rule of octet. So quickly, let me review the rules for writing Lewis structures, and then in the next part, we'll look at a few that we're going to write. So, the first rule is to determine the total number of valence electrons. So, for example, if we were looking at the carbon and oxygen in carbon monoxide, the total number, carbon has 4, it's a 4A element. Oxygen has 6, it's a 6A element. So the total there is 10. And then you start out, and then if you have an cation or an anion, you have to either add or subtract electrons based on that. And cyanide over here is an anion, so you not only do you have the 4 from carbon and the 5 from nitrogen, which makes 9, but you have an extra electron for that negative charge, so the total there is 10. Then you draw a skeleton structure around a central atom. Now in these two cases, there can't be a central atom because there's only 2 atoms. But when you have 3 or more atoms, you frequently have to select one that's going to be your central atom. And you connect each of those with a single bond. Each bond uses up one of your pairs of electrons. So if you start with 10 and you have one bond between the carbon and oxygen, that takes away 2, so you're left with 8 electrons. Then you distribute the remaining electron as lone pairs around the terminal atoms. So in this case, in the carbon monoxide case, you would take the remaining 8 electrons and let's say put 2 on the carbon or 4 on the carbon and 2 or 4 on the oxygen, and you would realize very quickly that you're not fulfilling the rule of octet in either of those. And we don't have an example of the central ion here, but I'll show you an example of this in the next part. And then lastly, if you're not fulfilling the rule of octet, then you can form double or triple bonds, which is what happened in both of these instances on the slide, in order to maximize the rule of octet.